Hi everyone, this is Group 8 and our project is named Transparent Hybrid User Adjustable Recipe Recommender System, and we call it Thursday. First, we're going to start off introducing some backgrounds. People actually use recommender system for recipe suggestions, and here is one successful business example called Kura Shiru, founded in 2016 and has already 21 million downloads. And the reason for its success, one of the reasons is its brilliant search engine using Amazon SageMaker machine learning models. Some related work we have come across when doing the research. One is very interestingly called Dynamic Next Baskets. So its pro is it can review users' dynamic interests at different times, but also keeps the all sequential feature of the user's consistent interest over time. And we have the famous neural CF. The pros of it is it really improves the accuracy by 5% because it was able to not just model the inner product but also takes the bias and learn from that. And here's a graph of rising popularities for the hybrid methods. We can see the shifts of trends of using the model from 2010 to 2020. Now it's a lot of hybrid being used. Here, therefore, to combine with the user research we did, now we came across with two pain points of the current recommender system's downfalls. One is a lack of user-controlled flexibilities, and the other is a lack of transparency, and we will address those two issues in our solution.
For the system design, we have user needs as our entry point passing to the entire backend called hybrid. The hybrid has 3 models and 1 post-processing part. Let my teammates first introduce the models first. We will come back to this later.
Stands for K-nearest neighbor algorithm. It is a collaborative filtering algorithm based on the simple principle that birds of the same feather flock together. That is to say that people who belong to the particular group are usually considered similar based on the characteristics they possess. And the advantage is straightforward, where this is a very simple algorithm where we can easily explain to the users, and also it's non-parametric, meaning we don't need to input any of the parameters. And the disadvantage is also quite evident, where it is a lazy learning algorithm. That is to say that it does not have a training phase, but rather memorize the training dataset, and all of the computations are delayed until classification. Therefore, the efficiency performance drops as the dataset size grows. So this will be a very hard problem, especially when we are dealing with a large dataset. And the second algorithm, or model, it is called SVD, which stands for Single Value Decomposition. It is also a collaborative filtering algorithm using matrix factorization technique. And the key is to distill data into essential components, or saying it reduces the number of features by reducing space dimensions. So the advantage is that by adding the regularization and bias term, it optimizes the model performance by minimizing the RMC error. So imagine we have an extreme case where a low rating given by a user to a recipe with no other rating available from this user, then this algorithm will minimize the error. And the disadvantage of this algorithm is that it transforms data into essential components, which may be difficult for users to understand.
The third algorithm is a content-based algorithm, but for this algorithm, we first have to train a word-to-vector model. In this model that can convert a word to a vector, the vector is dense, so it's different from the one-hot vector, and the meaning of the vector can be shown in the computation of the vectors. There is a well-known equation that the king minus man plus women is somehow similar to the queen. So that this is the basis of our embedding part. So in the embedding part, we are going to embedding our input and the data set ingredients as there are a list of strings. We are going to embedding them into a single vector. And before the embedding, we are we should to remove those stop words. The stop words contain those non-alpha inputs like the numbers or the Greek letters, and the measuring units like kilogram or lambs, and also contains all the common words. So like the word the or the word of that carries almost no meaning. And after getting the embedded vector, we are going to compute the cosine similarity of the embedded input with each record from the dataset. So the recorder is also embedded, and we are going to compute the cosine similarity and store them, and we finally return the top end result, where k is depend on the user input.
In order to have a good view of the hybrid system, we will review the user experience flow. Imagine that you are a new user to the website. You will fill out a pre-questionnaire where you are going to rate these recipes. After you finish, we're going to create a new user ID for you. The second part is where you can essentially have a influence on the entire recommendation system result. Contains the three inputs. The first one is you might want to include some ingredients. The second one is some ingredients that you absolutely do not want to see. And the third one is how likely you want to see other users' recipe who has a similar taste with you, where the user drag a rating bar and creates a value between 0 and 1. So far we have so many parameters. How are we going to make use of these values? So we go to the model activation. We pass some of the values to activate our three models in a parallel way, and we will get three separate lists at the end. How are we going to combine them? So we would have to calculate the weight assignment. Based on the input 2, we can calculate the weight we're going to give for the three models. And the next step is we will remove some unwanted ingredients. Essentially is the recipes that contains the ingredients that the user does not want. In the integration part, we're going to combine the three lists into one final list with the weight we calculated in the previous step, and you will see that if the model has a higher weight, it's going to display more elements in the final list, and also the position is going to be more on the top. Next, let me do an API demo for this on the back end. We have three cases in total. The first one is easy case. It does not have a similar taste need, so it's going to be the fastest because no KN SVD model is run through. There's no removal steps because the user didn't specify for unwanted ingredients. In total, it needs 2 minutes running, and the result is in a JSON file with the recipe names, ingredients, steps ready for the front end. For the average case, the user specified every parameter with the want ingredients, similar taste weight, and unwanted ingredients. In total, 3 models need to run 22 minutes, and you can see that there's a lot of squash because the user specified that they want more recipes with squash. Also, it does not have cucumbers and garlic because these are the ingredients that user absolutely do not want to see in this case. For the hard case, we're going to request more recommendations for a total of 20. By default, the required recommendation result is only 10. The model runs 31 minutes at the end, and you can see that the result is a longer JSON file because we asked for 20 recommendations result in total.
After the demo video, here comes to the evaluation matrix. The first part is for the content-based part, and here we show the two outputs from different embedding methods. And as you can see, the outputs are different for different embedding methods. They have different IDs here, as you can see. So we plot a cosine similarity graph for the top 50 records we have gained. And then firstly, as you can see, the TF and IDF methods, they have higher similarity scores. And secondly, the top 10 records here, they have very high similarity scores here, so we think they should be considered as good recommendation here. And the last one is that there is an obvious difference in similarity scores between the top records and the tail ones. This shows that our model can identify those records are very similar to the user input, and it can throw away those records are far away from the user input.
Okay, now so let's consider collaborative filtering evaluation metrics, and we divide them into three different sections, which are benchmark metrics, model-specific metrics, and cross-model metrics. We'll be discussing the green metrics in today's presentation. The first one is benchmark evaluation, in which we consider 5 different models in terms of their RMSE, feed time, and test time. And these algorithms are SVD, SVD PP, KM basic, slope 1, and normal predictor. And we can realize that the SVD has the lowest RMSE error, where the KM basic has the highest feed time and test time. Therefore, we choose these two as our standard baseline for our following experiments. So in our experiment, we tested our precision recall rates using the mark at K plot. And in both KN and SVD, as we can see in the graphs, that they perform so much better than the dummy random recommender or just a popularity recommender, which considers the most highly populated recipe IDs. So in these two models, the precision rate has reached around 80%, and their recall rate have both reached around 97%. So we consider them as the success models. And finally, we have our ROC-AUC plot, which is used to visualize the trade-off between true positives and false positives for binary classification. And the area under the curve, known as AUC, is used as an evaluation metric. So basically, the greater area of the semicircle, the better performance of the model is. So in this case, our SVD on the right has a slightly higher performance than our KNN on our left. And finally, I would like to introduce our cross-model evaluation metric, where we consider 3 different scores, and they are coverage score, personalization score, and intra-list similarity score. And finally, we were able to plot them in one single graph and compare KNN, SVD, and our hybrid algorithm Thursday. As we can see, although the personalization score and the intra-list similarity score for Thursday is not as good as KN nor SVD, it has a much greater coverage given the fact that it involves content-based filtering.
So in this semester, I would say each member of our group have learned a lot from both the front end and back end because we are the full stack development. As well, user awareness is another important lesson because we learn how to simulate the user scenario and do the research on what exactly the user needs. We also successfully learned how to build up a 1 semester timeline for our projects and to learn how to adjust the timeline with our current process. Definitely, our project is not perfect at this stage. So in the future, we want to create the ingredients object detection module and upgrade 3 control units to an NLP module interpreting sentences. We also want to implement the deep learning recommender systems and develop advanced features such as the time estimation, recipe uploads, and user profile creations. We want to optimize our front-end UI design to make it look better and generate a hybrid algorithm into the independent API for arbitrary datasets and the backend RS algorithms choices.